Welcome to module 3 of chapter 2. In this module, we will search for a simple formula which produces only primes. Formula which we mean a functions from integers to integers, and we look for functions from integers to integers whose range contains only set of prime numbers. And by looking different properties of prime numbers, then we will conclude that there is no such formula. Then later we will look for a possibility of finding primes up to a given real number x. This is what called prime number theorem. It is one of the famous theorem in number theory. After that, finally we will look for Fermat numbers and Mersenne primes. In this module, we look for is there any formula for prime numbers. Learning objectives of this module are: we will see large gap between the primes, prime number theorem, Fermat primes and Mersenne primes. Prime numbers have baffled scientists for millennia. Primes do not occur in any easily discernible order, which makes it very difficult to figure out whether a really huge number is a prime or not. Here huge number means taking thousands of digits long. Ever since the time of ancient Greeks, finding a simple way to prove a number is prime has been holy grail of mathematics, and the hunt has nearly driven several scientists mad. In 2002, 6th August, Manindra Agarwal of the Indian Institute of Technology, Kanpur, India, and two of his undergraduate students, N. Coyle and Saxena, distributed a 9-page paper that rocked the scientific world. They hit upon an ingenious algorithm that runs in polynomial time to prove whether a number is prime no matter how enormous. That is, number of steps is bounded by a polynomial function in the length of input data. In this problem, it takes a polynomial time to the number of digits in the prime. So, number of digits is the number. That means, we need to verify whether number is prime or not. Just we will see the number of digits in it, and the algorithm will produce whether this number is a prime or not in the polynomial time of the number of digits in that number. As the number sequence starts, primes are commonplace, as there is a little scope for small numbers to have factorizations. But as we go further down to the number sequence, the primes seem to become rare, but we do keep getting them. The thinning process of prime occurrence is, however, quite leisurely and surprisingly erratic. For example, 3, 5, 7 is the only trio containing 3 consecutive odd numbers that are primes, as every third odd number is divisible by 3. How to prove this? It is easy to see. If you take any integer a and if you evaluate a plus 2 and a plus 4, then it is easy to see that one of them is divisible by 3. That is, just we apply division algorithm. Then for example, if you take a equal to 3k or 3k plus 1 or 3k plus 2, then we will see that either a or a plus 2 or a plus 4 is divisible by 3. That here the proof. If a belongs to Z, then it is easy to verify that one of a or a plus 2 or a plus 4 is divisible by 3. The gap between two consecutive primes after first 2 is at least 2. So, the nth prime Pn is greater than or equal to 2n minus 1. The gap between two consecutive primes can be made as large as possible. This is what we called prime desert. That means, there is a large gap between two consecutive primes. That means, it is possible to, for any given n, it is possible to produce n consecutive composite numbers. So, how to do this? Let us assume n, small n belongs to capital N, that is natural number. Then we define m is equal to n plus 1 factorial. Then we have to show that, then we will show that m plus 2 is a composite number, m plus 3 is a composite number, and so on. M plus n plus 1 is a composite number. That is easy to see. It is because m plus 2 is divisible by 2. It is because m is equal to n plus 1 factorial. So, 2 divides m, 2 divides n plus 1 factorial. So, 2 divides m. So, 2 divides m plus 2 as well. So, 2 we can take 2 common from that. So, similarly 3 divides m plus 3 and so on. So, the proof goes like this. It is easy to see that m plus 2, m plus 3 and so on m plus n, and finally m plus n plus 1 are all composite numbers because of that. So, m plus 2 onwards m plus n plus 1, there are exactly n numbers, all of them are composite numbers. First m plus 2 is divisible by 2, m plus 3 is divisible by 3 and so on, m plus n plus 1 is divisible by n plus 1. So, number theories often dream of finding a formulas that generate primes for consecutive values of the integral variable n. Euler found one such formula in 1772. So, he defined E of n is equal to n square minus n plus 41. This is a quadratic formula, quadratic equation which yields prime for every integer n equal to 0, 1, 2, 3 up to 40. But it is easy to check that for n equal to 41, clearly it is not a prime number. It is because 41 square minus 41 plus 41, clearly it is divisible by 41. So, it is no longer prime for n equal to 41. So, but it is a nice thing that it is consecutively a prime number from 0 to 40. So, people try to look at other formulas like this, but they are unable to prove it. So, now we will give a general formula why we are unable to do that part. So, however, no one has ever been successful in constructing a polynomial f n that generate primes for all integers n. It is because we now will state that one, we will prove it, it is not possible in fact. So, that is the theorem statement. There is no non-constant polynomial f of n with integral coefficients that takes just prime values for integral n. That means, here in the place of n we will take only integers. So, f is a mapping from integers to integers. So, we proof goes like this, let f of n is equal to a k n power k a k plus a k minus 1 n power k minus 1 and so on plus a 1 n plus a 0, where all the coefficients a 0, a 1 and so on a n are integers. Here a k is not equal to 0, it is because we are assuming a non-constant polynomial. Also assume that f of n takes only prime values. So, that means we are proving by contradiction. Actually, we have to show that it will not produce only prime numbers, but we are proving in a contradiction. That means, we are assuming f of n takes only prime values. So, for a fixed m belongs to z, f of m is also prime number. So, say let us say f of m is equal to p, p is a prime number. Let us assume that here f of m is positive. So, then f of m plus t p, which is equal to a k into m plus p t whole power k, a k minus 1 m plus p t whole power k minus 1 and so on plus a k times m plus p t plus a 0. So, now if you expand it, if you use binomial theorem, then it is easy to see that this simplifies to f of m plus p into q of t, where q of t is again a polynomial with integer coefficients. So, now we already know that f of m is equal to p. So, this is equal to, that means that p divides f of m plus dp as p is equal to f of m. Therefore, using assumption that f takes only prime values, f of m plus dp has to be p for all t. If it is another prime, then it is a problem, it is because p is dividing f of m plus dp. So, it has to be equal to the same prime p for all t. In that case, what happens is, if you consider a new polynomial g of t is equal to f of m plus p t minus p, then it is easy to see that this is 0 for all t, as f of m plus t p is equal to p for all t. So, g of t becomes 0 for all t. That means, the polynomial g of t contains infinite number of roots, but this is not possible, as this is a contradiction, as any polynomial of degree k can have at most k roots in z. Now, after failure of finding simple formula for prime numbers, the struggle has started to find a formula which provides a number of primes less than or equal to a given real number x. So, here what we are saying is, if we want to find number of primes up to x, where x is any real number, x need not be an integer. So, we will define this formally. The definition, let x belongs to R, that is x is a real number and x is greater than 0, then pi of x, it is a new function pi of x. What do you mean? Pi of x means we denote the number of primes p that are less than or equal to x. For example, the only primes p less than or equal to 10 are 2, 3, 5 and 7. So, we have pi of 10 is equal to 4. Similarly, one can calculate pi of 100 and so on to check whether what is that pi of x is giving. Now, here is the table of values for pi of 10 power I, where I from 2, 3 up to 10. It also contains known approximations for other values of pi of x, approximations of pi of x. For example, x equal to 10 square 100, the number of primes up to 100 are 25, 10 cube, that means number of primes up to 10 cube, that is up to 1000 there are 168, up to 10 power 4 there are 1229. So, this is the list. Now, the above approximations are based on so called prime number theorem, first conjectured by Gauss in 1739, but not proved till 100 years. 100 years later, in 1896, it is given by Hadamard and Vallée-Poussin. So, this is one of the result which take a lot of time to prove, and further it uses all the other branches of mathematics, techniques from other branches of mathematics. So, this is a statement, the prime number theorem statements states like this: pi of x is asymptotically equivalent to x by pi of x for all x greater than 0. What do you mean by asymptotically equivalent? That means that limit x tends to infinity, pi of x by log x tends to 1. That means pi of x if you call it as a and x by log x if you call it as b, then limit x tends to infinity, a by b is equal to 1. That means these are not, pi of x is not exactly equal to x by log x, but what it is says is as x becomes larger and larger, then pi of x is very very close to x by log x. Therefore, we note that even though there are long stretches of consecutive integers containing no primes, but the proportion of primes till any particular number x behaves as a function x by log x. This is one of the nice observation. It is not only observed by Gauss, it is also many people observe Gauss, for example, Legendre, many other people, but Gauss stated in a systematic manner, but he unable to give the proof of this theorem. It is because till now what are all the techniques developed in number theory is not sufficient to prove this theorem. So, his student Riemann tried to solve this problem. So, in the process he developed many concepts in complex analysis, then by using those Hadamard and Poussin able to prove this prime number theorem after many years, means after almost 100 years later, and later people tried to find elementary proof for this. Elementary proof means that only using number theory techniques is it possible to prove. Yes, people proved that part also. So, in this way, in a way the above formula states that about 1 in log x, numbers up to x are prime when x is very large. For example, to understand what it means, for example, around x equal to 10 power 6, we expect 1 in 14 numbers to be prime, and around x equal to 10 power 50, we will expect 1 in 115 numbers to prime. This average thinning out according to a logarithmic law, but of course, this is only an average thinning out. In the year 1850, Chebyshev proved that for a sufficiently large x, there exists a comma b belongs to R such that a is less than pi of x by log x is less than b. Shepshu tried to prove prime number theorem, he almost proved, but he is unable to give exact complete proof of prime number theorem, but all his methods later used by the people and solved. So, in the process he himself introduced many arithmetic functions called number theoretic functions. If time permits, we will look at those things as well in this course. He also showed that if the limit extends to infinity phi of x by x log x exists, then it should be 1, means he given almost all the ingredients required to prove prime number theorem. As we observed, primes does not follow any particular pattern. There is no non-constant polynomial from integers to integers which produces only primes. Any non-constant polynomial, its range contains infinite number of composite numbers, that one can prove very easily. Now, we look for a special numbers where it is possible to find a necessary and sufficient condition for them to be prime. One way to find large primes is to look at numbers that have some special form. For example, numbers of the form a power n plus 1 or a power n minus 1, it is easy to rule out some values of a and n. For example, we have let a greater than 1 and n greater than 1, then a power n minus 1 is prime only if a is equal to 2 and n is prime. And similarly, a power n plus 1 is prime implies a is even and n is equal to 2 power k for some k greater than or equal to 1. Proof follows like this. We know that a power n minus 1 is equal to a minus 1 into a power n minus 1 plus and so on plus a plus 1. This result we proved in our first module. So, one can refer that. And now, note that if a is greater than 2, since in the statement of the proof, if you observe a is greater than 1 and n is greater than 1. So, we have n greater than 1. So, then a minus 1 is greater than 1 and a power n minus 1 plus a plus and so on plus 1, then clearly it is greater than or equal to a plus 1. Since a is greater than 2 and it is an integer, so a plus 1 is greater than 3. So, both the factors in the equation 1 are greater than 1, thus a power n minus 1 is not a prime. Hence, if a power n minus 1 is a prime, then a must have a equal to 2. Now, suppose that 2 power n minus 1 is prime, it is because now we confine a equal to 2. So, no need to take a other values. So, a is equal to 2. Now, suppose 2 power n minus 1 is prime, we claim that n also need to be prime. So, in this case we will prove by contradiction. So, let us assume n is equal to st, where 1 less than or equal to s less than or equal to n and 1 less than or equal to t less than or equal to n, then 2 power n minus 1 is equal to 2 power st minus 1, that is 2 power s whole power t minus 1, and this is a prime. So, again this is possible, that this is possible only if 2 power s becomes 2. It is because we already proved that a has to be equal to 2 in a power n minus 1 to be prime. So, 2 power s is equal to 2 only. So, that is equivalent to s equal to 1, that means t is equal to n. So, that is if you replace a by 2 power s in the equation 1, we will see that 2 power n minus 1 is prime only if s equal to 1. So, consequently t equal to n, hence n must be a prime number. This proves first part of the theorem. Now, we will go to the proof of part 2, that is if a is even, we will see one by case what happens if a is even. If a is greater than 1 is odd, then a power n plus 1 is greater than 2, which is even, and hence a power n plus 1 is not a prime number, thus a must be even. So, we have to prove in this proof that a should be even. So, we proved that if what happens if a is greater than 1 and it is odd, then we are getting a contradiction. So, because a n plus 1 is no longer a prime in that case, so a has to be even. Now, we have to show this n is of the form 2 power k for some k belongs to n. So, we first show that n is even, then later we will show that n is equal to 2 power k. For that, if possible n is greater than 1 and it is odd, say n is equal to 2m plus 1, then a power n plus 1 is equal to a power 2m plus 1 plus 1, that is equal to, it can be written as a plus 1 into a power 2 m minus a power 2 m minus 1 and so on a minus a plus 1. So, this identity is easy to show. Consequently, whenever n greater than 1 is odd, the number a plus 1 is greater than 1 is a factor of a power n plus 1, and hence a power n plus 1 is not a prime. Now, we will suppose that n is equal to 2 power s into t. We ruled out n is odd case, so n has to be even, but later now we have to rule out when if you take n equal to 2 power s into t, we have to rule out t greater than 1. So, let us assume t is greater than 1. Then in the similar argument, we just now we proved a power n plus 1 is equal to a power 2 power s power t plus 1 gives a contradiction to a power n plus 1 being a prime. So, we must have t equal to 1, and that is same as n is equal to 2 power s. So, we proved this theorem. So, now with this theorem, we are going to define Mersenne primes and Mersenne numbers, as well as Mersenne primes and Fermat numbers and Fermat primes. A number of the form mn is equal to 2 power n minus 1, n greater than or equal to 2 is said to be Mersenne number. If mn is prime, then it is called Mersenne prime. A number of the form fn is equal to 2 power n plus 1, where n greater than or equal to 0 is called Fermat number. If fn is a prime, then it is called Fermat prime. One may prove that f0 is equal to 3, fn is equal to 5, ft is equal to 17, f3 is equal to 257 and f4 is equal to 65537. They are all going to be primes, but as n increases, the numbers fn is equal to 2 power n plus 1 increases in size very rapidly and are not easy to check for primality. But luckily, with our advent of technology, by using computers, we are able to calculate that the next 243 Fermat numbers are known to be composite. So, now there is a conjecture that the only first 4 Fermat numbers are prime. So, Fermat original thought that fn will be prime for infinitely many seems to be pretty far from the reality. So, now we will prove few properties of these Fermat numbers. Let fk is equal to 2 power k plus 1, then f naught into f1 up to fn minus 1 is equal to fn minus 2. The proof we will prove by using induction on n. Base case, it is because we are assuming, base case means we are assuming here f naught f1 up to fn minus 1. So, it is better to take n is equal to 2. We have f naught into f1, when n is equal to 2, f naught f1 up to fn minus 1 is nothing but f naught into f1. So, which is equal to 3 into 5, which is 15, which is equal to 17 minus 2, 17 is the second Fermat number. So, we have 17 minus 2 is equal to f2 minus 2, that is what we have to show. So, the result is true for base case n is equal to 2. Suppose the result is true for n equal to m, that is f naught into f1 into epsilon and so on, fm minus 1 is equal to fm minus 2. Consider f naught into f1 and so on fm minus 1 into fm, which is equal to, we have to use induction. So, we will divide this f naught f1 up to fm minus 1 into fn as f naught into f1 into fm minus 1 into fm, but the result is true for n equal to m case. So, f naught into f1 up to fm minus 1 is equal to fm minus 2. So, and into fm. So, this is equal to, so fm minus 2 is equal to what? That is 2 power m minus 1, and fm is equal to 2 power m plus 1. So, this can be written as 2 power m plus 1 minus 2. So, we got this is equal to fm plus 1 minus 2. So, we proved the lemma. Now, we will prove another result, which is also one of the important properties of Fermat numbers. For distinct positive integers m comma n, the Fermat numbers fn comma fm are relatively prime. The proof will, in order to prove their fn and fm are relatively prime, that means that we have to show that their GCD is 1. So, let us assume GCD of Fn comma Fm is equal to D. Also suppose that n is less than m, it is because we have to choose one of the integer, either n or m is not less than or greater than. So, we are assuming that n is less than m. Then D divides Fn, since D is the GCD of Fn comma Fm. So, D divides Fn and D divides F0 F1 up to Fn into Fn plus 1 and so on Fm minus 1. So, that is nothing but Fm minus 2 by using previous result. So, D is dividing Fm minus 2 as well as Fn. So, D divides their integer linear combination. So, D divides 2, but we already observed that these Fermat numbers are odd numbers. So, D has to be equal to 1. So, D equal to 1 follows from the fact that Fermat numbers are odd. Note that we already proved that if Mn is prime, then n has to be prime. The first few Mersenne primes, here Mn means Mersenne primes, the first few Mersenne primes are 3, 7, 31, 127, 8191 and so on, which corresponds to primes 2, 3, 5, 7, 13, 17 and 19 respectively. Note that M11 which is equal to 2 power 11 minus 1, that is 2047, which is equal to 23 into 89. This is not a prime number. So, all Mersenne numbers need not be prime. Over the years, people have continued to work on problem of determining for which primes P, MP is equal to 2 power P minus 1 is a prime. To date, 48 Mersenne primes have been found. It is known that 2 power P minus 1 is prime if P is one among the following 48 primes. So, the table gives all the Mersenne primes, and also this is these are, if you substitute any of these primes in 2 power P minus 1, then that is also a prime. So, Mersenne prime number, that is M at 13466,917, it is also a Mersenne prime which was found in November 14, 2001. The decimal representation of this number has so many digits. It was found by team of Michael Cameron, George Waltman and Scott Kurowski et al. As a part of great internet Mersenne prime search. So, one can see Chris Caldwell page for more on this topic. This prime could be the 49th Mersenne prime in order of size, but we will only know this for sure that when GMS completes testing all exponents below this one. The current largest known prime is 2 power 57 lakhs 885,161 minus 1. It has so many digits and was found in January 25, 2013 by the researchers from University of Central Missouri. The most basic question about Mersenne primes is, are there infinite number of Mersenne primes? In this module, we observed that there is a large gap between two consecutive primes. On the other hand, because of Bertrand postulate, which is not stated till now, which guarantees the prime between n and 2n. Now, we in this module we stated prime number theorem, but we not proved. It is because it is one of the theorem which heavily depends upon other branches of mathematics. Now, with this we end this module.